My background is varied. I've majored in electrical engineering, physics, kinesiology. I have a master's in biomedicine. I also attended medical school. I'm published in the fields of molecular cell biology as well as motivational counseling. That's kind of all over the place. I've worked at a physics internship. I've worked for the Department of Defense. I've been a teacher at different levels. And then most recently relevant to you guys, I wrote a physics book. I wrote this because one of the things I fell into and that I enjoy most is teaching. And I wrote an AP Physics book because I wasn't happy with how the structure of a lot of the existing review courses and books, they were more like big books, like a 300 or 400 page textbook, but it didn't do a lot to coach students into how to answer the questions. So the whole purpose of the book is getting you used to the test. So like the tagline is, I'm not here to teach you physics, I'm here to teach you the AP Physics test and get you used to some of the ways they format the questions. Because I've seen far too many people who really knew their physics, but then they see the questions and they're like, I don't know what this is asking me, Will. What do they even want me to do? That's the purpose of what I'm up to right here. And yeah, let me know what else you want me to fill in before we start. And I will check the chat window too. Here, I'll leave the chat window open so I could see folks. All right, there's your chat. That's great. So should I just, okay, I'll wait for your cue.
So I think we're ready to go. Let's go, guys. And feel free to type any questions you have into the chat box. And we're looking forward to a great hour of learning what this AP is all about. And thank you so much for giving us pages from your book, which you hand wrote, color coordinated, and designed. We are so excited that we get to get a little inside peek. I'm going to go on mute right now. Okay, go ahead, guys.
All right, are you going to take care of admitting, etc. then?
Yeah, I'll handle the admit room.
All right,
no problem. Okay, go ahead.
So what I wanted to do, what I thought was the best use of our time is to give you all like a sampling of different types of questions that they're going to give you and the expected answers. So I picked 3 different topics to go over. 2 of them come from the 2019 exam. My speculation based off of what I've read on the College Board is that you probably heard that last year it was completely like short answer. This year I'm expecting it's not going to be quite that, according to the College Board. They still had derivation questions, etc. So I think it's going to be somewhere between the realms of what the 2020 exam was and what the 2019 exam is. So what I would like is the best way everyone's going to learn here is we have to do active learning, right? Passive learning is you just listen to me, you follow along, and you're like, oh, that makes sense, right? Better you write and you predict what's going to go on. So I want to jump right into solving problems right away. And again, anybody could type into the chat window and ask me questions or stop me on anything at all. This is meant to be your session. I have no idea where you guys are at in your class. So you let me know and I adjust, okay? So I just want to make sure the chat's working. Can somebody say hello? Can a couple folks say hello in the chat window? I just want to make sure. Thank you. A couple more folks. Just want to see if I got people alive and ticking back there. Hello, hello. Good, good, good. All right. Thank you all. So at least 3 is decent. It's a decent start, huh? All right. So what I'm going to do is this is an excerpt directly from the 2019 exam, and take a look at it, and I want you to read it. I'll give about 2 minutes. I want everybody to read it and then begin it. Read it and then think about it for a second. So, and everybody can see my screen okay, right? My screen share is working well. You have a nice clear view. Please, somebody let me know. Okay, thank you. So yeah, take a look here. And what I do is I have an artist tablet. I write on the screen. So it's extremely accurate. So there won't be any, you know, I'm not drawing with a mouse. Okay, so it should be very readable. And my notes I will provide for you after too. Well, we'll send them to you.
Where did you find this artist tablet?
This is the Wacom Cintiq Pro 16. There's a bigger one out there, the 22 and the 24. This one is discontinued because nobody wanted the 4K screen at the higher one. There's another one out there which I could recommend. It's only about $700. This one was about
So
$600.
this one, this tablet was 1600.
This tablet is $600. There's one out there for $700, which isn't quite as good, but I could discuss that later. Okay, so please read it, and I'll mute myself so you guys can think. All right, I'm just going to begin speaking then. So there's a trick to this one. I rather like this question because of how it makes you think. So here's the key thing. They want the speed of the center of mass. Now, I find the AP exam doesn't mean to be tricky at all. What they're trying to do is just make sure, do you really get this? They're trying to really ensure, do you really understand what's going on here? So we have this difficulty, right? We have two blocks here. We have this block, which is moving to the right with a constant force, right? Then we have this block, which is stationary. Now, you should be looking at the first block and saying, oh, from position A to B, in this vicinity here, it's moving with a constant force. And whenever you're doing your justifications on any AP exam question, if you can reference a relevant equation, they love that. It's a simple way to milk for points. If you ever look at prior answer guides that they have online, they will literally have like 1 point. Did the student mention this equation or this principle? 1 point. Do you know what I mean? So if you get used to speaking with equations, it's a great way to milk for partial credit. Even if you don't know what you're doing, it's a great way to milk for partial credit. So in this instance, we say, oh, in vicinity A to B, it's moving with a constant force. And remember, F is equal to ma, right? So a constant horizontal force means a constant acceleration, right? Constant acceleration. And I'll make a note here. So here's part A. And again, I'll send you guys my notes afterwards, but I also recommend you write along with me. So a constant acceleration means a constant change in velocity over time, right? So in vicinity A, block 1 is moving with a constant, constant acceleration means a velocity changing at a constant rate. But don't forget, there's also this mass here, mass 2. So you have one mass moving to the right, mass A, while mass B is stationary over time. But the net movement of the two of them together, the center of mass of the system, is net to the right. So we would draw an arrow like this. Here, I'll try to be neater. So there's our first vicinity here. The system is moving to the right initially. Make sense? And anybody can shoot me a quick question if you all want me to stop. So again, the trick is, oh shoot, there's two masses here, but don't worry. Just because one is accelerating to the right, the net of the both of them is changing its velocity. Now in vicinity B to C, so take a look here, it's lost contact with the plunger. So it's no longer accelerating, but mass A is still moving to the right while mass B is stationary. So we got right here, we have a net movement of the system to the right. Like that. The system is still moving to the right at this point. Now, in vicinity C to D, and again, these are all very typical tricks and things they put on the exam. They say, oh, in this vicinity here, you encounter an area of friction. And similarly, we can look at part B here. Well, we have a friction force, and of course, F is equal to MA. So we got a force of friction, which is going to serve to decelerate it, right? It's going to decelerate the system. Now, even though it is only affecting block A, if you affect one aspect of the system, you're still affecting the net system. So we are decelerating from here to here. And OneNote is going to try to auto snap. Let's see if I could avoid that. Decent anyway. Let's try this one more time. And then I'll just move this. So I'm moving it here. By the way, the relative positions of things are the only thing that matters, right? You don't need to worry. There's no calibration here on the scale. You don't have to go this high or that high. Just make sure you're showing that the net system decelerates. Now, here's the interesting thing. This is where I think some folks will get tripped up. At this point here, at position D, you got the block moving to the right. But you have this block just sitting here, stationary. Now, we know that after it decelerates, this part's easy. That, okay, it's just going to keep moving to the right with a constant velocity. But now the question is, what happens when block D strikes and sticks to block 2? Well, the interesting thing at this point is the net movement of the system is unchanged. The net movement of the system is unchanged. So this means that we're not going to lose any velocity. So it's a little bit of a trick, but this thing keeps moving to the right at the same way. So you might be tempted to explore conservation of energy, etc. But the thing is, this was not the whole time. It was how are block 1 and 2 moving together as one. It's not like an inelastic collision where you have a bullet, it's moving to the right, it strikes a block, and now the two move together. Kinetic energy is lost, etc. The two were considered the whole time. So any questions on that, feel free to type it in. I was going to put that here, but I just I annotated it above. And again, I will send you these notes if there are any questions. So anything at all before I proceed? Let me know if I need to speed up or slow down or anything like that. Even though we only have an hour, I hope to teach you something. Okay. Now, let's look at part B. And the biggest thing I want to teach here with part B is how we might milk for partial credit and some of the things they look for. So go ahead and read part B and let me know, let me know if you have any questions before I begin it. I'll give you about 1 or 2 minutes to read it. Now, it's typical that when you have a subpart, of course, it builds off of the initial thing. Now, as it was stated initially, you're frictionless initially, right? It's initially frictionless. So remember that the only thing, just reviewing the torque equation, I don't know if you guys have, I have a quick question. Let me ignore this. For part A, how come gravitational force can be ignored? Well, the thing is, it's not that it's ignored. It's that it's never changing its position, right? It's never changing its height relative to the ground. So the gravitational force in some sense is used here because that's what's creating. If it were not for the gravitational force, you would not have a force of friction here, right? There would be no friction interaction between the block and the surface, right? There must be gravity. Because here in quick review, remember you would do something for a flat surface. FF is equal to mu Fn. And if the surface is flat, well, then that's equal to mu Fg. So in some sense, the gravitational force is incorporated there, if that makes sense. Please feel free to post a follow-up question as I proceed. Now, the plunger is returned to its original position, so blah, blah, blah. So now we have an interesting situation. This vicinity here is frictionless. Now remember the torque equation. Torque, which is indicated with the letter tau, is equal to the perpendicular force times the distance. At least this is my way of writing it. So the force applied perpendicular to an object times the distance to the lever arm. I won't go into that in too much detail. We do not have time for this today. But so here's the key thing. There has to be a force, right? And the only thing that could supply a force to cause the ball to rotate, in this case, is friction. Now, we have a ball here that is sliding along a surface frictionless for most of its journey until it hits vicinity C to D. Once it encounters, Control C, Control V, once it encounters it, this is going to exert a torque on the system. And the distance to the pivot is the radius of the ball. And so there's a force, a perpendicular force times the distance to the ball. So in short, the only place that the angular momentum can change is when there's a torque applied, right? Does that make sense? So, so remember angular momentum, just to review, angular momentum is equal to the moment of inertia times angular velocity. So the only way we could change angular velocity, omega, is with a force. And again, I realize this is moving relatively quickly. Let me know if there's follow-up I can do for it. But I can change angular velocity with force. And if I change the angular velocity, I thus change L, which is the angular momentum. Now, I just want to give you guys some hints onto how you might answer this and how you would justify it. And you would say something like this. Angular momentum is, you could even put equals I omega. In order to change omega, there must be a torque applied. In vicinity C to D, there is friction. This will apply a torque and thus change the angular momentum. Notice the way in which I speak the answer. It's a because of this equation, therefore this. It's a safe way to answer any of these questions. Justify with the equations, justify with the principle. Your partial credit, those guys are looking for it, right? Remember that the people who are grading these are grading hundreds of them, right? So I used to be a teaching assistant myself for college. And when I'm grading 300 papers, I don't care how good your English is. I don't care about any of that. All it is I have 5 points to award for this question. And I'm saying, did the student mention this? Did they mention this? Did they mention this? Did they mention this? Okay, 5 out of 5. Next student, right? Oh, they only mentioned 3 of my 5 key points. Okay, they get 3 out of 5. Next question, right? Learn to write your answer like a test grader wants it. Any questions about this? I was going to skip to a rotational motion problem next, one that I wrote that you can't find on prior AP exams. Maggie, have I addressed your question, by the way? And is there anything else I can address before I move on to the next one? Feel free, take a minute or two and type your questions. And Francis, should I admit the other person in the waiting room? Anything at all, kids? Nothing? Feel free, it's open forum. When we have a smaller group, it'd be cool we have a little bit more interactivity. Okay, so moving on, rotational motion. So this is a question that I wrote. And take a moment to digest it. I really like, for problem A, I wanted to write a question that would capture everything that I think is very typical on an AP exam. So I'll pause. Okay, this one is meant to be tricky. We have a difficult situation here, right? We have a mass which is accelerating, well, which is going to go downward, right? This mass is going to be pulled down by gravity. And that is going to exert, that's going to pull on the rope, which is a force of tension, right? And that tension is what's responsible for accelerating the cylinder, right? That cylinder is going to unravel slowly over time. So if I were to look at, we'll start with part A. It says, derive an equation. Derive an equation to describe what is going on here. We got this mass, which is pulling down, which is going to unravel the string around this. And this is a, massed cylinder. And they give you, I give you the moment of inertia of the cylinder. It's 1/2 mr². So if you're stuck on a derivation, this is the number one thing I recommend, is you start saying, just jot down equations that might relate to it. So you would say, okay, I need to make an equation that has alpha by itself. And it has to be in terms of m, big M, little m, r, a, and any physical constants. Okay, does this make sense, I hope? Okay. So, well, okay, there's a torque here, right? We can start with the torque. Torque is equal to force times distance. And torque is also equal to moment of inertia times alpha. And now our goal is we need to make an equation that has only alpha, but we need to only have M, R, and A. So we have a problem, right? We don't have things in terms of M, R, and A yet. We have all these other terms. Now, don't forget, you could set this equations, equal to one another that deal with the same variable. So you could say, look, force times distance is equal to I alpha. Any questions on this thus far? Just jotting down equations, trying to go through it. And let's go over some things here that are occurring. So you guys might recognize that this system here is basically a what you call an Atwood's machine, right? Two masses connected via pulley. So I'm just going to plop in a figure here. Just to remind you guys of this. So as it accelerates downward, there's a force of tension upward, which is preventing the mass from going in free fall. So we can make a equation for the big mass down here. So for big M, and again, I hope folks are following this. Please write something in there if you need. But for the big mass, you have, we do F net equals MA for it. And I'm going to call downward positive to make my life easier. So you got mg acting downward, force of tension acting upward. And that's equal to, don't forget we're talking about this mass, so I call it big MA. Right? That's for that mass. And I'm just going to do something really quick. I'm just going to rearrange this equation to solve for f of t. So we got mg minus ma equals ft. Just a simple rearrangement. Now, this is nice. Well, look, I got some terms here. I've gotten rid of ft. I've gotten rid of ft, which was one of my goals, right? ft was not one of the variables that they said our equation can result in. So now we have to recognize, I will put the equation earlier here. Force times distance equals, what the one we derived earlier, equals I alpha. Now you have to recognize that the force of tension is the only thing responsible for causing this mass to accelerate, right? So that goes here. That's mg minus ma times distance is equal to I alpha. Lovely. Some other things, by the way. So I'm going to give you like a top-down view of the cylinder. So here we go. So here's a top-down view of the cylinder. And notice that the distance to the pivot is the radius of the cylinder, right? You know, this string is wrapped around the cylinder. So we say, oh, okay, the distance to the pivot is the radius. So that's another variable I can plug in there. So we got mg minus ma times r is equal to I alpha. So now we're getting more variables plugged in that they wanted. But we still have this pesky I here. And this actually isn't so hard. So they give that to you. Remember, you are not expected to know what the moment of inertia is for any object. They will provide that for you if you need it. So, but you have to just understand what is the concept of moment of inertia, and that it's dependent on the mass and the distance to the pivot. So they give you that I is equal to 1/2 mr squared. So we can plug that in as well. This is, I love using parentheses when I plug in, 1/2, and it's the mass of the little cylinder, which is little m, mr squared times alpha. And so here we are, mg minus ma times r. And then now we could do just some simplifications. I could distribute my r. I won't, but I'll just make a point here because you'll see why I don't need to in a second. There's my r. If, you know, this r over here cancels out with this r here, so I'm left r squared becomes r. And then now I just get alpha by itself. 2 times the quantity mg. Oh, I made a mistake here. This is ma. mg minus ma equals, no. Yeah, right. I multiply by 2 to get rid of that. And so that's going to be r alpha. Sorry, mr alpha. And then now I divide both sides by little mr. That's your rotational acceleration. My final answer is in terms of all the variables they specified. This must be done. So when you derive an equation, if you have any variables remaining that they didn't say were okay, you will not get full credit. Any questions at all on that? I hope I'm still working. Y'all hear it? It's just, this is so quiet. I'm not used to this. All right. And by the way, any topics, I can continue on this. Are there any topics at all that you all are covering right now, which you would like me to discuss? Because I can continue on this problem, or I could do something else. Somebody give me a vote. Anything at all. Somebody's got to send a vote in, and I'll continue. Because I'm also still hoping that I'm online with everybody here.
Guys, or you can also type in the chat box, William, you're awesome, just keep going. So that's also an option, okay?
Yeah, type it in the chat box, please. Anything at all, any other topics? Because if some of you guys haven't covered rotational motion, I don't want to plow you into this. Could we talk about free fall? My class is talking about that. Okay, let's do a little thing on free fall then. So I'll come back to this if you all want. So let's see. So you're talking like kinematics, right? I take an object and it's up here and it's in free fall, right? And typical assumptions are there's, no air friction, right? It's an object in free fall. So it's going to accelerate at a constant rate under the influence of gravity, right? Where A, oh, and by the way, just a thing to save you guys some time, you are allowed to use -10 meters per second squared. They will give you full credit if you use that. Might as well, it'll save you time of making a simple calculator mistake, right? So you need to, they do give you these equations, but you need to know these off the top of your head, because the multiple choice section, they don't give you the equations. So you have to know this. So you have to know that V final velocity is equal to initial velocity plus AT. And V final squared is equal to V naught squared plus 2A times distance final minus distance initial. And then we have something like D final equals D initial plus V initial T plus 1/2 AT squared. It's got to be like that off the top of your head. So, you know, there's tricks they give to these things typically. They might say, let me try to generate an equation, and hopefully I can address this. I'll try to do something a little bit like a projectile motion. So, and I'll just make this up off the top of my head. Let's say you have a ball and you throw it up in the air. And I'm showing it in an arch, but let's just say you throw it straight up and down. And you give it an initial velocity of, we'll say, 10 meters per second. And you're 50 meters from the ground. And now there's some questions we might ask. I'll throw two of them out there. A, what is the max height that the ball reaches? What is the max height that the ball reaches? Okay, so when you do this, you just get used to what they call the big three. Some people call them the big five, but I don't think those other two equations are useful. These three are fine. Just know these three. So what's the max height that the ball reaches? Well, if you're comfortable with these equations, this is pretty straightforward. Here's your initial position. Here's initial, here's final. So we would say, okay, we're trying to solve for max height. Well, what's the quantity wanted? Max height is D final, right? This might help you say, okay, equation one is out of this. This is not too helpful. So you would say, all right, I'm trying to solve for D final. If I tried equation 3, the problem is that I don't know what time is. I can't figure out, I couldn't use equation 3 right away. I could solve for it, but that's not going to be immediately useful. So we use equation 2. Especially as you're getting used to it, I recommend you write out the equation because it helps avoid plug-in errors. And then we take advantage of the fact that at the top, at the projectile's apogee, that the final velocity is 0. So we would say, oh, okay, at here, at the top, it's 0. They gave us the initial velocity, it's 10 squared. Don't forget for acceleration, you plug in -10, right? Because it's downward relative to the projectile going up. And then we look for D final minus D initial. It began 50 meters up, so we use 50 there. So now we would do 100 minus 20 times D final minus 50. And now it's just some algebra, right? So this would be -100 equals -20 times all this nonsense. Why distribute when I could first divide? It makes my life easier. 5 is equal to D final minus 50. And hooray, it ends up at a final height of 55 meters. Hopefully that helped. Sophia, any direction you want me to go with something like this? Would you like me to discuss we could solve for the total time it's in the air. Is there another direction that anybody would like me to go with this, or any other topic that I can slam out in 5 minutes? I'm open. I'm an open book. Total time, no problem. So this is a good one because most of you, I picked an asymmetrical situation because most of us are used to a symmetrical situation, right? This is a totally acceptable curveball they'll throw you, because you'd be like, oh, total time up is equal to time up is equal to time down. Yeah, that's if it's symmetrical, but this is not symmetrical. We have a different distance up than a different distance down. So what you would need to do, what I would recommend to be easiest, is calculate the two times separately. So I'll write this down. Part B. What is the total time the ball is in the air? All right, well, do two things separately. So I'm going to say section 1. Section 1. Ball begins at top of hill and goes to its apogee, its highest point. So we calculate it thus. So we're calculating time. Pretty straightforward here. Let's just use equation 1. So V final equals V naught plus AT. So 0 is equal to 10 minus 10t. Yay, I picked nice numbers. 10t equals 10. We got t equals 1 second for it to make it all the way to the top. So the first part of the journey here, I'll do that in blue. It takes 1 second to make it up there. 1 second to make it to its highest point. Now, it's got to travel back down. So we have to add the time it takes in section 2. Section dos. Time it takes to travel back down. So this is where it's useful to break it into sections. Now it's just a ball that began up here and is traveling down. But remember, it is 55 meters. It's 55 meters above the ground, right? It's 55 meters up in the air. So now we can't use equation 1 anymore because we don't know V final, right? We don't know how quick it's traveling the moment it hits the ground. Equation 2 is also out because we don't know V final. But let's use equation 3. So D final equals D naught plus V naught T plus 1/2 AT squared. Well, it's going, this is the initial position in this section. Here's the final position down there, right? So D final is 0. D initial is 55. Well, this is an object. This thing here, remember, this is going to be 0 because it began, it's an object that here, we'll use my little 3D printed octopus, okay? It's an object that I threw up in the air at its highest point at apogee. Its vertical velocity is 0, right? And then it falls back down. So at that point, its velocity is 0, and then I plug in the rest. So plus 0 plus 1/2. Gravity is downward. Don't forget that. Negative 10t squared. I'll fly through this quickly. Negative 55 is equal to negative 5t squared. So that's going to be 11 is equal to t squared. Of course, calculator for this. So we would say square root of 11. Boom, there you go. 3.3. By the way, they don't usually care about sig figs here. So t is equal to 3.31 seconds. But now, again, this would be, if I were grading this, I'm guessing this would be a 4-point question, just so you know, for this part anyway. If you got to here, if you showed me this and this would be worth probably 3 out of 4. You have to recognize that you have to add sections 1 and 2. So you have to add 1 plus 3.31 seconds. and that's equal to 4.31 seconds total, right? So the trick to kinematics things is know your three equations off the top of your head. Know how to apply them depending on the situation. Know when things become zero. Also remember that I only dealt with this in the vertical direction, right? You have to specify each equation's application to the vert or the horizontal direction, because there's different physics. Well, not different physics, but there's a different vectors going on in each direction, right? Of course, we know that these are things that have probably been drilled into you, that if you have a projectile and you project it through a parabola, the parabola, boom, you know that horizontal velocity is constant, but vertical velocity is constantly changing. It becomes zero at the top. And at this point, if you're in a symmetrical situation, the vertical velocity is the exact opposite of what it was at the initial part. What else you guys got? I don't know if we go till 9 or 9:10. I am uncertain, but I'll keep going. What do you got? Throw something at me.
We're going to end at 9:10, but we definitely want to hear some like closing tips with the AP and why we should join the course. I think that would be great because we are looking to get a group together for the course.
Sure. So let me say this, like the structure of my class is thus. First of all, you know, we'd have a smaller group. We'd interact a little bit more. I'd put out assignments and try to help you guys make sense of this. There's a couple of key components. One of them is I do rapid review because this is a review book. Like I'm still, people write books as if kids will read them all. You know, read the whole thing cover to cover. I wouldn't. There's no way I would read a book cover to cover at that age. I still don't. So the whole structure of it is like, I'm going to cover only the topics you need as fast as possible. Like, let's review what these are. Here's the rotational, and I try to make analogies. I'm like, hey, look, remember your vertical equations are just like the rotational ones. It's the same thing. Rapid review of concepts, understand what centripetal force is. And I try to do things, I often try to cover a concept in just one page. You know, everything you need to know about centripetal acceleration and torque, I try to knock it out as fast as I possibly can. Because I know we're not going to have time to read it all. That's crazy talk. And then we go into immediate application because you don't really get a thing until you applied it to a problem. Now, the other really important thing that you'd have to be good at is I coach people into how you milk partial credit. I wrote my book structure around how the AP College Board grades things for partial credit. And so even when I wrote my own problems, so there's a lot of problems in the book that I also cover in the course that you'll never find anywhere. They're only in my book and in the course. So I coach you into how an AP test grader gives you partial credit. And the majority of my students, by the way, this is always true. The majority of my students get 4s or 5s. And it's mostly just because, again, I've had plenty of A students, but being an A student doesn't mean you're an A student on the exam. It's how do I teach you to take this test? And my strategy is pretty straightforward. I do review and then we just go straight at old exams. And then after you see like 4 or 5 derivation questions, you start to get the pattern, be like, okay, first I do this, then I do this, then I do that. When you're writing an experiment, you get used to, okay, here's an experiment question. How do I format this? If I'm designing an experiment from scratch, what do they even want me to do? When I write my answer, what sort of key points should I hit? And everything I do, I cover. the cool thing about it is if you have the book as well, you listen to me, you take your own notes, but it's also there in the book. So you have a way of kind of double checking everything. Like I want a student to have multiple ways of going at a problem. You know, this is multimodal approach. Let's see, what else? Any other things? If you want to throw a question in there, you can. Otherwise, I'll go over a quick experiment problem if you guys want that. And so here we'll look at, let's bring up the 2019 exam. So here we are. I'm just going to look up an experiment question. So this is blocks connected across a pulley. Okay, here we go. So in this one, you're asked to, this is going to be a design and experimental procedure thing, which you'll see in part B. Now, what trips students up is, what do I write for what part of the question? And you just have to get used to doing, you have to go out and do sample questions. It's really the best way to prepare. Because sometimes it doesn't even make sense what they want, but when you get used to it. So we have here a situation where we have a sphere and it's on this spring compression apparatus, and it says, okay, when the spring is compressed, the plate can be held in a pin by any of the positions A, B, or C. And so there's a steel pin that fixes it in place. Great. The sphere is launched upon release of the pin. A student hypothesizes that the spring constant of the spring inside the launcher has the same value for different compression distances. Now, the student plans to test the hypothesis by launching the sphere using the launcher. State a basic physics principle or law the student can use in designing the experiment. So for part I, I'll just clip this. Let's see. I'm just going to clip this and throw this in my notebook. So here we go. We're going to plop this in here real quick. Delete this real quick. Boom, boom. Here, let's paste this here. State a basic physics principle or law. Well, you could say, I would take this whole thing, this whole apparatus, and mount it vertically, just to make it a little simpler. So we have a spring that's wound up. Here's the ball. I'm not showing the different positions, but I'm going to launch it up in the air. One simple principle we could use is I could use conservation of energy. And so literally for part I, you don't have to over answer it. Say, use the conservation of energy. But here's the thing. You'd be tempted to only leave it at that, but you don't answer part I. You answer all of part A together. So part 2, which is also part II, which is also part of A. Using the principle or law stated in blah, 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 determine an expression for the spring constant in terms of quantities that can be obtained from measurements. Okay, so we use conservation of energy here. You know, the initial energy, E initial is equal to E final. And initially, when the spring is compressed, that is 1/2 K x squared. And at its maximum height, see, what we could do is we could take this whole apparatus, we could mount it vertically, and we could measure what is the difference in the height as I launch it from different compression distances, A, B, and C, right? And so if I mount it vertically, by the way, this is not the way the College Board did it. They did it horizontally. I think it's easier to do it this way. So I would go 1/2 kx squared is equal to the potential energy mgh. And so as this changes, this changes. Now, derive an expression for the spring constant in terms of the quantities that can be obtained from the measurements, blah, blah, blah. So you're not done here if you leave it like this. They want it in terms of K. So you do a quick rearrangement. And I'll just do this. This would be 2GH over X squared. That's going to give you full credit. Hope that helped clarify some things. So notice,
William, it's already 9:08, so
Sure.
we're gonna just wind down. Everyone, you can go off mute and you can say thank you, or you can type thank you into the chat. But we definitely want to give you a big, huge moment of gratitude because you took your time and you really made it work for us. And you're all the way out in California. Where in California are you, William?
Santa Rosa, we're not far from where the fires were. They were 2 miles from our house.
Oh my goodness. So
yep, 2 miles.
we really...
But we're happy now. We're safe. You're welcome all. It's up to you. I'll give like 5 or 10 minutes to answer a couple brief questions if anyone wants to hang out and just ask me something. I'll give you additional help. But so the last thing I want to say about this course is, like, I try to keep it interactive too, and not only cover things, but I adjust. I have a general strategy. Whatever you guys want, I adjust around. If you want to take more time on this topic, no problem. We'll have 20 total sessions. And so even if you guys want to cover things relevant to your class beyond the course, I could do that. So any brief questions that anybody has before we go?
It's already pretty late. It's
Okay.
9:10, so they're probably all going to clock out.
You guys are probably fried, huh?
Yeah, but I definitely think everyone's going to give you a big, huge thank you. Okay.
All right.
Thank you so much. All right.
You're welcome.
Bye, everyone. Thank you. Thank you for participating. You're welcome to go off the mute and say thank you, or you can type it in the chat. But I think I actually like taking a screenshot when you guys type thank you. It's a cute little memory that we have, and I'm going to send it over to William so that you have it as well. Okay.
Right.
Thanks, William. I'm really glad that you were able to make this time, and we're good. Okay.
All right.
Thank you, William. Thank you. So if you want, William, you can close the chat, or if I'll close it, it's up to you, whichever one goes.
I'll let you, you're the boss. You do it.
Sometimes.
How do we get the notes? I'll tell you what, I'm going to export those to a PDF right now, and then you'll have them. And so I'll export them to a PDF. I'll give them to Francis, and then you'll have what we covered today. Okay?
Perfect. All right, guys, enjoy. Thanks, everyone. Okay, bye.
Bye-bye, y'all. All right, there's that. And okay, stop share.